Alright, in this video we're going to take motion graphs and we're going to look at how do we work backwards. When I say backwards, I mean how do I find a position time from a velocity time graph? Or how do I find a velocity from an acceleration and then a position from a velocity? So working backwards is a little trickier, and I'll show you why in a second. Most of the work we've done so far, we've taken a position graph or a velocity graph and deduced them to find velocity and acceleration. And the key was the slope, right? If I knew how the slope was changing and where the slope was positive, negative, or zero, I could then derive the shape of this graph very easily. We are still going to use slope working backwards, but we'll see that it's not quite enough to give us all the information we need. So let's look through an example to try to figure out why. Alright, so let's start with a velocity graph that starts positive, crosses zero, and then moves into negative. So the first graph that's easy to derive is the acceleration graph, because it's just the slope of this graph defines the acceleration. So my acceleration is, the slope is negative and constant, so my acceleration is negative and constant, because acceleration is the rate of change of velocity over time, which by definition is the slope. So at some negative value, my acceleration is constant, because the slope is negative and constant. Alright, well that way it gets pretty easy after a while. You've hopefully gotten good at that. But what about my position graph? What does my position graph look like? Now, if we use the same idea, this idea of slope, right, we can get the shape of the graph, and I'll show you how we find the shape. I know that my velocity starts as positive, so since the slope of my position graph tells me velocity, the slope has to start positive. As time goes on, by the time I reach this time, where it crosses zero, I know the slope has to be zero. And then as I move farther in time, the slope has to be negative. So if I start with a slope that's positive, right, it's going to be positive, flat, and negative, I begin to see that I'm going to have some kind of downward curved quadratic. That's fine. I can get the shape from that. But the question is, well, where do I draw it, right? And here's where there's limitations in working backwards. If I look at one analysis I can do off of the velocity time graph is finding the area. The area will tell me my displacement. Okay? What displacement measures is change in position. Okay? What it doesn't tell me is absolute position. So what I mean by that is I would have to provide some additional information to know exactly where this plot is going to be. I know how it changes over time, right? I can know the displacement from this graph. I can get a numerical value for that, but I don't know where it is. So let's take two examples. Let's say I started at a position of negative 20, right? Or I started at a position positive 10. Once given an initial condition, now I can say, all right, I start with a positive slope, I go to a slope of 0, and I end with a negative slope. So I start positive, and let's say at time about here, I'm flat, so I'm curving downward. And I know it's quadratic because when this is linear, this is quadratic from working the other way. And then it slopes down like this. Okay? Negative slope, positive slope, 0 slope. Positive slope, 0 slope, negative slope. Same would come at an initial position of 10. Positive slope, 0 slope, and then negative slope. So these two graphs have the exact same shape, they're just located at different positions. And for those of you that are going to go on and take calculus, this is a property of integration. Integration, when you integrate from one graph to the other, from taking the area is a form of integration. When you integrate, you pick up a constant term. So when you go back and learn that next year in calculus, you'll say, well, that makes sense. I pick up a constant, and that constant term defines my initial condition, my initial x naught, my position. All right, well, let's look at another example. How about working from my A graph to my V graph and then back to my position graph? So we know that if my A is positive and constant, that my V graph, the slope is positive, and constant meaning it's linear. So I know the shape of the graph, but I don't know exactly where it is, because if I look at what I can solve for from finding the area under the AT graph, I can find the change in velocity. It doesn't tell me absolutely what the velocity is, it just tells me the change. So I can have a negative velocity and have a positive change and get less negative. I can have a positive velocity and have a positive change and get more positive. So what that means is I have a increasing linear sloped line, but without being told I start at rest, or I start at -20, or I start at +15, right? It could be any of these lines. I could shift anywhere along this axis, because again, when I integrate, I go from AT to VT, I pick up a constant of V naught, which, I mean, I could show you that real quick, where that comes from, integrals, and this is just a brief aside for those of you that are going to take calculus down the road. If I write acceleration as change in velocity over change in time, which is also can be written dv dt in calculus terms, essentially a dt equals dv, and if I integrate both of these, I get v as a function of time is equal to a times t, because you pick up a t, plus some constant v naught. Right, so this defines the shape of the graph. This defines the constant at a time of 0. What's my initial v naught? These are my v naughts. So it's a property of integration. All right, anyway, same thing goes for xt. All I know from this positive slope is the shape of this graph. Now it's going to be looking different depending upon whether this is my line, this is my line, or this is my line. So let's just look at the 3. Let's plot the 3. Let's start at the +15 with a velocity that's +15 that keeps increasing over time. So I'm going to start with a slope of, you know what, this is going to get really messy if I try to do all these. Let's define this as the velocity graph and then ask what are the options for my position graph, because I pick up another constant in integration back. So if I start with a +15 velocity and then I increase over time, I start with a steep positive slope that gets steeper. But I also don't know where that is. So it could be here at a +10, it starts positive and then gets more positive. Or here, -10, starts positive and gets more positive. So the shape would be something like this if I'm going from this one. But it would be shifted upon the axis depending upon giving you my x naught variable. And if you want, I might as well show you that integral too, just in case you're curious. So we know that v as a function of time is v naught plus at. If I integrate this, I know that v of t is just dx dt, so I put the dt over here. Right. Integral of dx is x as a function of time, and then I've got v naught times t plus 1/2 at squared plus some constant. Don't worry, you will not need to know how to do this in this class. But if you notice, what I've derived also are 2 of our big 3 equations using some calculus. But this is where this x naught term comes. It defines where I am along the axis, where my initial condition is. So in summarizing, going backwards, in order to know the shape, I can use the slope, all right, and how the slope is changing from positive, positive, 0, 0, negative, negative. The slope can give me the shape, but I need to know some initial condition to know absolute position on the graph. So if given a working backwards graph, you have to ask yourself, do you know the initial conditions? Do I know the initial velocity from an A graph? Well, then I can plot it. If I know it starts at rest, my velocity is 0, and I know the acceleration graph, well, I can plot it from there. But without the initial condition, you're only guessing as to where it is absolutely located on that line.